So Nathan said to the left. Sure. Right. I think here we go. Current going in. Very good. Nathan. All enough, right. So nice. Right. So north to south. Right. And magnetic field going north to south. Currents going in. So therefore it's left hand row. Magnetic field going north to south. Current going in. So it should be going inwards. So the forces. That way. So just a finger a little kind of weird. But it had to stay like this. Your finger pointing down like that. Okay. So this is the principle behind photo. All right. So before we look at the actual photo, I told you last day that if I were to take a current carrying conductor, so I have a magnet here, right? Again, magnetic field is going north to south. And if I were to place a conductor in the middle here, but instead of one single conductor, I am going to place a rectangular coil, right? And I'm connecting this coil so that current will flow here and current coming down here. You'll see that? So current flowing up here and current flowing down here. Right? I'll draw the rest of the diagram just now. Okay? So I want to show you now what will happen on either side of the coil. All right? Right, let me see. Who I'm bringing to help me with it now? Here. Come here, man. All right, so this come quick. So here's what we're trying to work out. We are trying to figure out what direction the force acting on here, right? Because remember, there's a current carrying conductor, right? When a current carrying conductor is placed in a magnetic field, it'll experience a force. You okay with that? This is a current carrying conductor in a magnetic field, so it will experience a force. All right? Let's see how that force is going to create something for the motor. Go ahead. Use the left hand rule here and tell me what direction the force will go. Well, just take out your left hand, right? Nice. Set it up now. Magnetic field is where? North to south. North to south. Nice. Current going where? Don't move them. Right. Current going where? Up. Right. So let us think up. Point up.
So it's gonna be other way. Yeah.
Are looking right? No, the current will go like that. Right. So the force going where? Right? So the force acting, she got the force acting downwards there. Right? It's a kind of 3D thing. So the force acting here, downwards. Work out here now. This side. Let me see where you get. Right? No. Current first. Current going what? Downward. Right? So make this finger go down. This weird finger keep it like that. Right. So the force acting where? Up. So it acting down and it acting up. Right? So imagine this. Imagine there's a downward force here and an upward force here. What will happen to this? That's okay? So it will go here, then when it reaches here, same thing will keep happening. Right? So if a downward force acting here and an upward force acting here, and that continuously acts, it will cause it to turn. Okay? And the principle of a simple motor is what? So, take it. Right? The principle of a simple motor is to take electrical energy and give you mechanical energy. Are you okay with that? You see how it works? Yeah? No, yeah? Go next one. Go on next one. Motor. Right? So watch it here. You follow how I get down and up here. Using the rule. magnetic field north to south, right? Magnetic field going north to south, current going up. So therefore the force on this side is down. And the force on this side is up. So imagine this is the rectangular coil. If a force acting downwards here, and a force acting upwards here will cause it to turn. That's okay? But the problem with the motor is that current have to stay in the same direction all the time. Otherwise, you will not experience the same forces, right? So they have other components. There's a component called a split ring, and I'll show you just now on the simulation. Right? And this split ring is connected to a little carbon brush, and that is connected to battery. Positive, negative. Current going this way. Right? So a simple motor looks like this. Magnet, coil, battery, split ring. Okay? So I'm going to show you about the simulation from last day. Let's see if it makes any sense, right? Oh, sorry, that's online. You're seeing that? Online. You're seeing the screen.
Yes, sir, we seen it.
Nice. Who are using the mic there? Somebody actually using the mic? All right, nice. Right, look at that simulation there. Right? You're seeing the magnet? You're seeing the magnet, the North Pole and South Pole, one red and one blue, right? You're seeing the coil. Right. Look within the coil, you're seeing the rings. So imagine you have a big circular ring, but you split the ring in two. You're seeing the split ring there? So the split ring connected to the black wire. Right? Which is the rectangular coil. Are you okay with that? Right? And then, well, those are silver things there, the brushes. That doesn't move, right? But you see this? You see those half a circles there? Those move with the coil. All right? So before I do anything, you all can figure out what direction it's moving in. I'll give you a little help. The magnetic field moving from so North Pole is the red and the blue is south. See if we can figure out what direction that coil is going to move. If it's going to move clockwise or anti-clockwise. Think about it. Think going to move clockwise or anti-clockwise. North is red and south is. Okay, clockwise or anti-clockwise? And going this way. So looking like clockwise. Looking like the same thing on the board, right? So the right hand side here. The right hand side here will go up and the left hand side will go down. Right? Yeah. Let's see. Where is it going? What's up next? What's it up? Yeah. That's anti-clockwise, right? But okay with that? Everything else, okay with that? Right? Exactly what we did on the board. That's in there. Yeah? Anybody can see how it works? Right? But there are two small things in between there I want to identify, right? Look at these. Look at these split rings, right? Look at these split rings and I'll stop it at a particular point, right? Look at it there. Right? You see these split rings are the darker gray parts. Right? In that particular location there, the split rings not touching the carbon crystals. Right? So it looking something like this. Something like that. You see that there? Right. But if it's not touching the carbon crystals, then no current will flow. So therefore, this part here will no longer be there. If that happens, then no force exerted. Right? But what is here? Well, when something is vertical, because of inertia, it will continue to flow in the same direction. So when it reaches here, inertia will pull it downwards. Right? So it will not stick up here. Inertia will pull it here, and then the force will continue to be exerted on it. All right, so we have to explain all of that. Because when it's in the vertical position there, no current flowing in it. Right? No current flowing in it. So therefore, we cannot use the rule anymore. So when it's vertical, inertia will pull it downwards. And then it will continue to exert. All right? Give it up. And I want you to notice. I want you to notice, look at the current direction here, right? Current flowing positive to negative. You see that? I'm going to let it flip again. When I reach next side, same thing, right? Positive to negative. So is the current direction changing? No. Is the magnetic field direction changing? So the current staying the same, magnetic field staying the same, then this will always stay the same. That makes sense? So if that happening, then the force exerted is always in the same direction. So it will always flow like that. Okay? You don't want that photo behaving like this. Okay, and then come back here. You don't want that. All right? Because it will not have a good exchange of electrical energy. All right? Are you okay with that? So the principle behind a photo is to take electrical energy and give you mechanical energy. Are you okay with that? All right, so I want you to draw this, please. Right, and I'm going to give you some steps that we're going to look to explain. Exam, they'll give you a diagram and to explain how the photo works. All right. So I'm going to give you 4 things to remember and explain, and then I'll give you a note. Can we understand how it works? Sure, we can make it clear how the waves are falling. Right? Yeah, we have to explain how the whole thing works. So this one going. Now one going like that. And then upward force here. And upward force here. And downward force here. And going down here, up here. So it's in like that. Yeah, southern this side, northern Africa. The same thing, the same as everyone. So there's a downward force here, an upward force here. It's kind of weird because it's a 3D diagram, right? But I'm here. Ask some questions. Online, ask the questions, please. Am I here? Am I here? Right, so let me start over. You have your north, you have your south, you have your current direction. Are you seeing that the force on this side is down? And the force on this side is up? Left hand rule. Magnetic field going north to south. Right, so I'm gonna take it off. We never said something wrong before, but it's still this direction and clockwise. Right? Both of them are the exact same thing. Right? So watch this here. Right? Don't know why this screen is so small. Whatever. Right? So magnetic field north to south. Right? Current going A to B. So the force on this side is down. That's okay? Yeah? Right. What is down? Correct. So your force on this side is down. It matches as a 3D diagram, right? So the force here is pulling it inwards. Huh? That's okay? And then this side, do the same thing, and the force here is upwards. Okay, now? So the force here is down, and the force here is up. So yeah, so the current coming down, magnetic field north to south, so that's the force. Right. Right. So here the force is down, calling inside here down, and up is this way. So the force will turn like that. See enough? So if I have a diagram here, it will be going down here and up here. So it cannot turn in anti-clockwise. That's okay? But remember, it's really a 3D thing, so it's not really going like that. It cannot go inwards. Right? That's okay? You sure? Right? And the reason it's turning this way all the time is because this current, because of these rings, allowing the current to flow in the same direction all the time. Right? Because in the current direction, current going this way, right? If by chance current change direction and go this way, then the force will be other way around, forcing it to go clockwise. You don't want that. You want the motor to continuously go in the same direction. You okay with that? So the problem is they don't really ask you to draw it in exam. The problem is they will say, take this diagram and explain how the motor works. Okay? So we have to find a way now to remember a proper explanation for this. Right? I'll go it over and then I'll give you some guidelines that we're going to use to create our explanation, right? So how do we explain this? Number one, before you start to explain, I'll give you all this, right? So don't write it down. Let's make sure it makes sense, right? Right? The first thing that we need to do, of course, is label everything. These are called split rings, right? These are called carbon brushes. That's your supply, right? Then use your supply to show them the direction current, right? Positive, negative. That's okay? So you show them the direction current. But before you do that, label it up. A, B, C, D. So you're telling them current will move A to B, then current will move C to D. That's okay? Label it poles, make sure you know where it's north and south. Are you okay with that? After you have everything labeled, the next step is to use Fleming's left-hand rule. Use Fleming's left-hand rule on AP, and then use Fleming's left-hand rule on CD. And tell them the direction that the force is going to be exerted. That's okay? That's the order I wanted to go in, right? So when you use Fleming's left-hand rule, you'll tell them that AB experiencing a downward force, CD experiencing an upward force, right? Causing it to turn in a anti-clockwise direction. That's okay? Right. That's a pretty hard part. The easy part now is to remember two phases. When the coil is vertical, you have to tell them inertia allows the coil to turn to the opposite side. That's okay? You have to explain all that, right? Because when the coil is vertical, the problem is what? The coils, sorry, the rings not touching the crushers, so no current flowing. Right? So you tell them when the coil is in a vertical position, right? Inertia allows it to go to the opposite side. Right? And when on the opposite side, current still moves in the same direction. Are you okay with that? There's one thing I want to point out before I give you the notes, right? No? Where you get lost? Huh? Oh, well, watch this here. When it goes, when here comes down, right? One more time. Last time. Right? When it's here, right? And this will experience a downward, upward. And when it reaches here, this side comes here. Right? And DC will be on this side now. And AB will be on this side now. Right. So it switch, right? But the problem is, right? The problem is that when DC on this side, current still going up. And when DE on this side, current still going down. Right? So current still going in the clockwise direction. Everything working out. But when I say other side, I simply mean CD on this side, AB on this side. That's all. And it will continuously keep changing. All right? But current going in the same direction because of difference. All right? So I'm gonna give you an explanation on that now. Oh, actually, you know what to do? I'll make you guys want to. Right, so before I give it in pencil, see if you can jot down the 5 important steps. Yeah. Or 6, or whichever you have. So in pencil, see if you can write down the important steps and make it down. Then I will give it to you. Right. Number one, current direction, label it up. Right? See if you can write down 5 steps. They help explain the reading motor. Right, what do I change this thing? I'll go back to first. See if you can write down your own steps and trying to explain it, right? Right, you should have at least one after your label. You should have current direction, then you should have that. Then you should have explained what's happened here, and then what's happened here. But 4 or 5. 4 or 5 steps. Coming, right. That's the case of one of your steps, right? Yes, that's about 5 steps. If you have 3, well, at least you have 3 out of 5. Right. If you look here. No, yeah, just log out. Oh. That starts. Right. Anyway, so I wanted to show you this example here. I really like this example because it shows you these steps that you're going to need to explain, right? You'll recognize This is the motor. You've seen everything. Magnet, the slip rings, the split rings, the labeling, everything. You've seen that? Nice. Look at what it gave you here. Explain what happens when the switches close and they give you the order. Number one, direction of current. Number two, forces acting. Number three, apply the rules. Sorry, any rules applied. Number four, direction of rotation. Number five, how continuous rotation is achieved. Those are the steps that you have to have when you explain it. All right? So write that down. Number one, direction of current. Number one, direction of current. Number one, direction of current. Number two, forces acting. Number two, forces acting. Number three, any rules applied. Number three, any rules applied. Anybody had this type? No order. Number three, any rules applied. Number four, direction of rotation. Number four, direction of rotation. And number five, how continuous rotation is achieved. And I just set up number five into two parts, right? Number five, how continuous rotation is achieved. So I want to break up number five into two parts. Part A, when the coil is vertical. Part A, this is 5A. When the coil is vertical. And B, when the coil is on the opposite side. And part B, when the coil is on the opposite side. When the coil is on the opposite side. Okay? Nice. So here's the exciting part now. You get to write an explanation and you'll read it now. I'll tell you to get 9 marks. So use those 5 steps, write your own explanation, and I'll tell you. I'll listen to it and I'll mark it one time. Here, come the phone. Go ahead, up one. You have 6 minutes. Okay, you 8 minutes. Now, 2 minutes, don't let you tell all the answer. Right, you do after an essay, right? You answer each point. That's all I have to do. Point form good enough because when we mark question, we don't mark the essay, we just mark, we have pointers, right? So there are 5 important things, make sure that. And you do like Clemens, left hand, left right hand, good. 5 steps. Oh yeah. I'll start in the back, I'll put somebody in the back there and come down. Right? Try quick. Who? David. Go. What's the name again? Yes, she understood. It's all true, right? Let's see how it is. I go and how we really make it. Like if you use left hand rule or if you use right hand rule. You know how to use that rule? So you get the force direction. Right. So you got it right up. Yeah, you wanna read yours? Website link there. So it's that 4 and 5 general. On your phone, it cut to that all. Yeah. Right, can I hear one? Anya, I'm going to videos. Yeah. Yeah, yeah. Now, yeah, listen. Now I finish. Again, you have 2 minutes again. Now I finish. All right. Huh? Right, so to try to explain the way it works, I don't want you to memorize the essay, right? Just remember those 5 things, and it should be all right. Right? Let me read it. All right, so that's the way the motor works. Now we're going to switch after this. We're going to go from the motor to the generator. Right, on the motor, just make this little note. Note that right, note that the motor converts electrical energy. Note that the motor converts electrical energy into mechanical energy. Note that the motor converts electrical energy into mechanical energy. And that Fleming's left-hand rule is also called the motor rule. Fleming's left-hand rule and that Fleming's left-hand rule is also called the motor rule. Okay, that's just 2 little things to note, right? All right, let's go, David. Make a mistake there. How we get current direction? No, current direction comes from here. Plus and minus. So the current direction goes from A to B and C to D. Okay? So you can see the current moves in a clockwise direction. That's okay? You have to say that, right? So current moves in a clockwise direction. Huh? No. Right? Current here goes in a clockwise direction and use the labeling A to B and C to D. Right? Next. I'm going to get 2 other forces now. Right? So the interaction between the magnetic fields of the conductor and the magnet causes a force on AB and a force on CD. How we found the direction of the force? Right, by using Fleming's left-hand rule, the direction of the force was obtained, and AD experience of downward force, right? And the CD experience of upward force. That's okay? I'll look at that here. And that was what, 4? 3. All right, yeah, so right, so let's make it simple. The direction of the rotation is anti-clockwise. That's all, right? So because here upward and here downward, it's moving anti-clockwise. Right, what's all here? It will not always be anti-clockwise, huh? If your diagram have current going somewhere else, or you have your south here and north here, you have to work it out, right? You have to look at the question that they give you and figure out the directions. Are you okay with that? So it's not always going to be clockwise, anti-clockwise. All right, online? Finally, so it's not always going to be anti-clockwise or current going to be clockwise. You have to look at your label and question and figure it out. All right, Annalie, Adrian. Are you okay with that? So it's not always going to be the same. Our example is the same so far. All right. So the coil moves in an anti-clockwise direction, and then 5A. 5A. What happens when the coil is vertical? Try to remember, when the coil is vertical, no current flows, but because of inertia, right, it pulls the coil downward. That's okay? And how is continuous motion obtained after that? When the coil on the opposite side, current flows in the same direction, so therefore, the coil will experience the same forces in the same direction. Right? I'm going to pull all 5 out now. Well, okay with that? Once they have those things, I will get out. All right, you can let it. I'm going to pull about what? Number one, current moves from the positive terminal to the negative terminal. Write it over. This is the explanation I want to have, right? Current moves from the positive terminal to the negative terminal. Positive terminal to the negative terminal. And on the coil, it moves in a clockwise direction. And in the coil, it moves in a clockwise direction. A to B, C to D. A to B, C to D. Yeah, A to B and C to D. Remember, some questions, these things are not labeled. You have to label it, right? Right? Label it on a question paper. A, B, C, D. Right? Current goes A to B, C to D. All right, number two. Because of the interaction, of the magnetic fields, of the magnet and the current carrying conductor, of the magnet and the current carrying conductor, forces are exerted on the coil. Forces are exerted on the coil. Three, by using Fleming's left-hand rule, by using Fleming's left-hand rule, we obtain the direction of the force by using Fleming's left-hand rule. We determine the direction of the force on the coil. By using Fleming's left-hand rule, we determine the direction of the force on the coil. And then if tell them AB experiences a downward force. AB experiences a downward force. Leave right in. AB experiences a downward force and CD experiences an upward force. AB downward force, CD upward force. Number four, this causes the coil to move in a anti-clockwise direction. This causes the coil to move in an anti-clockwise direction. Right, 5E, well, you don't have to write 5E, look at next point. Next point. When the coil is vertical, what's your number? When the coil is vertical, the split rings do not touch the split rings. Right? The split rings do not touch the brushes. The split rings do not touch the brushes. And hence no current flows in the coil. And hence no current flows in the coil. And hence no current flows in the coil. Full stop. Because of inertia, very important. Because of inertia, the coil will continue to rotate. INERTI. Which law is that? You done first law, right? Remember that? Huh? Well, it's not even. Fighters. What's inertia? Which first law? Newton's first law, right? An object that's moving will continue to move unless an unbalanced force makes it behave differently, right? I'll say that. It will continue to rotate in the same direction. And lastly, last point. When the coil switches sides. When the coil switches sides. When the coil switches sides, current still flows. When the coil switches sides, current still flows in a clockwise direction. Current still flows in a clockwise direction. Hence, all the forces exerted will remain the same. All the forces exerted will remain the same. Right? And allow the coil to move in a continuous direction. And allow the coil to move continuously in the same direction. I'm not changing it, so allow the coil to move continuously in the same direction. All right, that's all. Right? You might remember it perfectly word for word, but here what you remember: label, current direction, forces, force direction, vertical, want to go the opposite side. Right, just remember those points. All right. So I think I just start the generator, but next day we are going to learn Fleming's right-hand rule and generator. So your homework, read upon Fleming's right-hand rule and generator. Right, you can look at it.